Do you know how a file system is stored on your device? The files and the folders form hierarchical data and are stored in the form of trees. Hi, my name is Prateek, and in this tutorial I'll be teaching you the fundamentals of binary trees and the various operations that you can perform on trees. But before we move on, make sure you check out free masterclasses on Scalar's event page and learn from industry leading experts. Also, subscribe the channel if you haven't already. Let's dive right in. Let us start the topic by understanding what is tree data structure. So in computer science, a tree represents a hierarchical structure with a set of connected nodes, right? So for example, if you look at this diagram, this actually represents a tree, and this node, it is the starting of the tree. It is called as the root node, right? We will discuss where it can be useful. So in this structure, each node in the tree can be connected to many children. So this is a non-linear data structure. The first non-linear data structure that we are covering is a tree. So far we have talked about array, we have talked about linked list. All of those data structures were linear data structures because they were following a sequence. Here there is no sequence, here there is a hierarchy, right? So each node can be connected to many children. So 2 is connected with 7 and 5. It is connected with 2 children. So 7 and 5, they are children of 2, but must be connected to exactly one parent. So each node must have one parent. I cannot say 7 will have 2 parents. No, 7 will have only one parent, that is 2. 5 has only one parent, that is 2. 2 has only one parent, that is 7. 10 has only one parent, that is also 7, right? So except for the root node, which has no parent. So root node has no parent. Rest all the nodes, they have one parent, right? Now because of this property, there will be an interesting observation. Suppose you are creating a tree in which you are going to have n nodes. Okay, for example, I have 3 nodes here. So how many edges you will have? So except for the root node, for every node that you will have, that you will add, there will be an edge. So there will be, of course, n minus 1 edges in the tree, right? So in any tree that you are going to create, irrespective of is it a binary tree or not, each node that you add will add a edge in the tree except the root node. Okay, so root node does not add any edge in the tree except the root node. If there are n nodes in the tree, there would be n minus 1 edges. Okay, because root node has no parent, rest all the nodes that you add, they must be connected to a parent through an edge, right? So this is an interesting observation you can note. So in every tree there will be n nodes and there would be n minus 1 edges in the tree, right? So that is tree data structure. Now let us talk about where this data structure can be used, how it can be helpful in computer science. Okay, basically trees are used to represent or manipulate hierarchical data in applications such as file systems or directory structure, right? So all of you have worked with a file system. So what happens in a file system? You say, okay, I have my PC. In this, I have certain drives: C drive, D drive, E drive, right? And then inside this, I have folders: F1, F2, F3, F4. And here also I have folders, then I have subfolders, right? Maybe I have photos here, maybe I have some documents here, right? Now we often do operations like that. Okay, I want to move these photos from here to here, right? So what is going to happen? You're not going to copy this data, you're going to say, okay, I'll cut and paste. So if you simply want to move this photos from here to here, what you need to do? You do not need to copy this information to some other part of the disk. You only need to change the reference, right? That okay, earlier this reference was stored by F4, now this reference is stored by F2. Basically the links, right? The links to the folders and subfolders, they can be easily changed if the data structure is implemented using a tree, right? This is something we will discuss, right? So file system is a good example of a tree data structure, right? Multiple inheritance trees in programming. So this is used when you're using object oriented programming concepts and you have a class C which is going to inherit from a class A. It is also going to inherit some methods from class B, right? So this is not exactly a tree, I would say, because this node, this is inheriting from two different classes. So irrespective of that fact, basically the trees are internally used by the compilers to see what methods would be part of the class that you have implemented using inheritance. Okay, then again, in natural language processing, basically whenever you have a sentence, for example, I am going for a party, right? Now this sentence can be broken down into certain components. Maybe you have a verb, maybe you have a subject, maybe you have a predicate, or you have even for language parsers. Okay, so what are your parsers? Whenever you write code, it goes through a language parser so that compiler can figure out if there is any error in the code, it is having the correct syntax or not. So they again form a parse tree of that code, right? So again, it's an interesting concept that you will learn in compilers, right? So again, they are used a lot in understanding of the language. Okay, then in HTML there is a DOM tree. So whenever you open up a website, right, you see there is a HTML code, right? Inside HTML code there are a lot of tags. There is head, there is body, right? Inside body there is a paragraph, there is a div, there is an image, right? So if you look carefully, this whole document forms a DOM tree. So inside DOM tree you have head, you have body, right? Then you have certain elements, you have div, you have paragraph, here you might have image, you might have some text, right? Now what is happening? You want to say, okay, I want to click this particular button, and on clicking this button, this div will change its color, right? So how do you fetch elements from this huge web page? So there are methods like document.getElementById, by id, document.getElementBy by tag name. So what it is doing, it is traversing this DOM tree. It is a tree of objects. Okay, it is a tree of objects in your web browser. Again, it's behind the scenes. So it is doing some kind of search operation on this tree, and it is trying to manipulate this tree, right? For example, you scroll your web page and a new item is added from the bottom. So maybe it is adding something in the list, right? So your tree is getting modified, right? Then of course there are trees which are used in search operations like binary search tree. There are trees which are used to implement data structure like map, self-balancing trees. Okay, so they are used to perform faster searches and keeping data ordered. We will talk about BSTs in the coming class. In machine learning, there is a concept called as hierarchical clustering. So it is a part of a clustering technique, okay, where I want to group together similar items. So it comes under a part of unsupervised learning. So there also the tree data structure is used, right? So we see lot of applications are there, and that becomes very important for us to understand the tree data structure. So in this video, we'll be talking more about binary trees in general, because that they are the most common ones that are widely used. Okay, so let us start with binary trees. So let us start by understanding what is a binary tree. So as I discussed, it is the most commonly used tree structure in which you can have at max 2 children. Okay, so it constrains the number of children for each parent to at most 2. That means a node can have 0 children. For example, in this case, the nodes D, E, F, G, they don't have any children. They are also called as leaf nodes. The nodes which don't have any children, they are called as leaf nodes. Node can also have one child, right? Or it can have 2 children, right? It cannot have more than 2 children. For example, if I draw a few structures, you have to tell me whether it is a binary tree or not. Is it a binary tree? The answer is yes. Each node has 0 child, 1 child, or 2 children, right? Okay, is this a binary tree? The answer is yes. So this node, the node C, it has 1 child. A and B, they have 2 children, and D, E, F, they don't have any children. Hence, in this case, we have 3 leaf nodes. So this is again an example of a binary tree, right? Now what we are going to learn in this tutorial, we are going to learn about different operations. How do we create a binary tree? How does the node structure look like? How do we perform search or an update operation on a binary tree? How do we display a binary tree? And there are 4 popular ways to do it. pre-order traversal, in-order traversal, post-order traversal, level order traversal. Okay, so we are going to look at all these things one by one, and we'll be starting with creation of tree first. Let's begin with that. Let us talk about creating the tree. So first of all, we need to understand the structure of the node that is going to create the tree, right? So in this tree, if you look carefully, there are so many nodes, and this box represents one particular node. Okay, that is the root node, right? So I have the root node. Now what is this root node going to contain, or any node going to contain? It is going to store three things. One is your data, one is the address of the left node, one is the address of the right node. Okay, in Java we also call it as the reference, right? Now suppose this object B, it is created at some memory address, let's say 250, right? This is the location of B in the heap where it is created. So A's left is going to store 250. Let's say this is created at some location 380. So A's right is going to store 380, right? A itself is created at some location, let's say 400. The root is going to store 400. Okay, so root is not a node, root is just a reference to the root node. Okay, so root variable is holding the address of the root node, right? Now B is left is referring to D, so D is created at some location, let's say 560. So here we will have 560. Now D is left and right, they are null, they don't refer to anyone because D is a leaf node, right? So D is a leaf node, E is a leaf node, F is also a leaf node, so they are left and right, they are null. Now B is a node with a single child, right? Because it does not have any right child, hence this value is also null. And here I will store the address of E, here I will store the address of F, right? So I hope you are understanding the structure of the node. So I need to implement a class called node, in which I will have three things. One is my integer data. Data can take any type. Just to keep it simple, I'm taking it as an integer. One will be my node left, a reference of the next left node, and node right, a reference to the right node. If the left and right node does not exist, then I will set this value to null, right? Now let us see in the code how can I implement this node class. So let us go to IntelliJ. Now I am going to implement the tree data structure. I have a class called binary tree. I have a class called binary tree test. Both are empty classes as of now. So in order to build binary tree class, I need to define that what is node, right? So node will have three things. One is my data, one is my left, and one is my right. Apart from it, I also need to give a constructor here, that whenever a new node is constructed, what data it should take. Else, okay, data I will know, but at the time of construction of new node, I do not know what node will go into the left, what node will go into the right. So I will simply say that my data, this is equal to D, and left and right, they will be set to null by default. So whenever you're creating a new node, you do not know the left and right nodes. So these will be set later, right? Now comes the binary tree class. Now suppose we want to create a tree like this, okay, or let me take up another example in which I have numeric data. So I can say, okay, let me create a tree like this, 1 connected with 2, and then it is connected with 3, right? Let's say very simple tree, 3 nodes. Now how you will read this tree? The first thing is, how do I read this tree, right? So the first input I will get is the root node. Okay, user will enter 1. I will say fine, input is 1, let me read this, create a node called a root node, and root node is going to point to this node, right? And in the left of this, I will again read from the user, right? The user says okay fine, the next node is 2. So I'll say fine, I'll create a node called 2, I will attach it in the left of 1 like this. Okay, and now what is the next node I will read, right? Now it can happen that I have something in the left of 2, or I have something in the right of 2, or I have something in the right of 1, right? So I do not know. The way we are going to do it is, we are going to read now what is there in the left of 2. Okay, so if the left of 2 is null, right, I will input -1. So -1 in the input will denote that there is nothing here. So I will simply set this value to be null, right? What is right of 2? I'm again going to say it is -1. So I will set this value to null, right? Now this option is gone. I've read it. This option is gone. Now I can only read this. So I'll come back here. I'll say fine. This 2 is done. Now try to read what is there in the right of 1, right? So I'll say, okay, the next input is 3. I will create a new node and I will attach it, of course, here. But before that, I will read what is in the left of 3, right? So attach part will happen a little later, right? I'll read what is in the left of 3. So this value would be -1, -1. What is there in the right of 3? Again, I say -1. Now this node is constructed, or in a way I can say this subtree has been constructed. So once it is constructed, I will return it back to the parent. So the parent is 1. It will get connected here, right? So this will become more clear once I write the code. The idea is I will of course do it for a bigger tree as well. This is little tricky, right? So what the idea is, we are going to build a tree recursively. We are going to build recursively, right? Now how we are going to build a tree recursively? Many tree operations, they are recursive in nature, right? So I'll say, okay, fine, I will build the root node. That is 1. Then I will build the complete left subtree. In the above example, the left subtree has only one node, so it looks easy, right? I will build the complete right subtree, right? Okay, I will build the complete left subtree and I will attach it here. That is part 1. I will build the complete right subtree and then I will attach it in the right of 1, right? So we will do it for a bigger tree as well. So let us jump into the code first and try to see how this can be written. Of course, I will do a dry run and explain you how you can build a more complicated tree like this with the same code. Okay, so let us go into the binary tree class. One thing is for sure, that every tree must know what is the root node. What is the root node? So this is something that will be the property of the tree. Every tree must know what is the root node. Just like in a linked list, every linked list knows what is the head of the linked list, what is the tail of the linked list. So in case of tree, you must know that what is the root node, right? So one thing is there, I am going to read this tree. So user will input will come through the user, right? So let us see the tree construction part. So in this binary tree class, what I'm going to do, I'm going to first define the data members of the tree. So I have only one data member, that is the root of the tree, right? Now this root should be initialized. Where it should be initialized? Of course, when the tree is created. So when the tree is created, it is created when the constructor is called. So I need to define a constructor called binary tree, right? Now in this constructor, what I need to do, I need to take input from the user. So in order to take input, I will need a scanner object. I will say scanner SC, this is equal to new scanner system.in. So scanner object is used in Java to read inputs. So I have imported the scanner, right? Now the building of the tree is recursive in nature. So I will create a helper function to do it. So I can say fine node, let's say create tree, and to this create tree method, I'm going to supply the scanner object so that this method will actually read from the user. Okay, so I will say fine, the root should be initialized by calling the create tree method. So create tree is a helper method getting called in the constructor that will read the tree from the command line, right? Now I'm going to pass the scanner object here so that I can use it to read data from the user, right? I don't want to create this object again and again inside this method. Okay, so I'm creating it once and that object is being circulated across all the recursive function calls that are going to happen, right? Now suppose I read something, right? I can say okay, data that I'm going to read is scanner dot next int. So I'm going to read something. All right, now I have read something from the user. Let's say this data is 1, right? What I want to do, okay, this data can also be -1, right? I'm asking, okay, tell me what is the next data. So I will actually have a two types of case. One will be my base case. If my data is -1, then what should I return? Right? I will return a null. That means, okay, I don't want to attach any node here. That subtree is just null. So I will return null. But if it is not -1, if it is something else, basically I'm talking about the recursive case. For example, if my input is 1, what I will do, I will create a new node. I'll say fine I'll call it a node root. This is equal to new node, and I give it the value data, right? So if root is confusing to you, just call it as n, right? I create a node called n, which is initialized with this data. So suppose my input is 1, right? So I say, okay, n is a new node. Now what should I do? I need to read the left subtree. Basically, I need to create a left subtree here and attach it here, right? So what I can say that in the left of n dot left should refer to a new tree, which is equal to create tree. Again, scanner will get passed. What should n dot right point to? N dot right should also refer to a new tree called create, that is returned by the create tree method. And again, the scanner is going to get passed. And then I can return n. What I'm saying that n dot right should also point to a new tree. So left subtree, right subtree, right? This is the recursive way of constructing the tree. Now you might ask, okay, how does this method will actually work? I will show you it will actually work. Let's see how it's going to work, right? So let us take an example of a more complicated tree, or let's first start with a simple tree, right? Let's say I have a tree like this, 1, 2, 3, right? Now for this tree, what is my input going to look like? So input will be 1, then it will be 2, then it will be left and right of 2, which is -1, -1, then it will be 3, and left and right of 3, which will be -1, -1. So given this input, I actually want to create this kind of a structure. Let's see how it's going to happen, right? So I said fine, root is equal to create tree. I call this method create tree. It reads something from the user. So one integer it's going to read. So it's going to read 1. So data is not -1. Fine, I come here. Node n, this is equal to new node. So basically I have a stack call in which n is going to say n is a new node where the data is 1. Fine. Now n dot left, it makes a new call. N dot left, right? So I said fine. In the left of 1, I want to create tree. So again, create tree is called. If you come again in this function, you read something from the user. So you read 2. Fine. You said fine, I create a new node n. Okay, a new node n is created. So earlier n was here, now the new n is here, right? It's a local variable. It is created in every stack call, right? It is here. This is equal to new node where the data is 2. Fine. Now n dot left, this is equal to create tree, right? So again I make a function call, create tree, go and do something, right? So I've made a call for here, right? Now if I go and read what is the next number, it is -1. So I return null. Basically what happens? So 2's left made a call and it got a value that is null. So 2's left starts pointing to null. Now what is the next call that is going to happen? We are in this stack and I make a call that 2's right, this is equal to create tree. So I make another call here and this value is also null, right? Once these two calls are over, this one and this one, I return n. So I return this n back where I return it to the place from where it was called. So who called it? 1 called it. So 1 gets to know that my left should refer to this node. So by returning this n, this answer goes back to the previous function and one's left is now connected with. Now what is the next call we are going to make? So one's left is now created. So this call is over. One's left is now created, right? Now one says, okay, fine, my left is created. I'm pointing to 2. I will make a call to update my right. So n dot right, this is equal to create tree, right? So this was already read. Again, a new function call is made. You read the next number, that is 3. You create a new node from line number 29. You said the new node is 3. N dot left, this is equal to create tree. So 3 is left, makes a call to create tree, which again reads a data that is -1. So you return a null. So 3 is left, says, okay, make a call. That call says I will return null. Now 3 is right, says make a call to create tree. It goes and reads a number that is -1. Again, it returns a null, right? And then you return n. So now n is this, right? So it returns 3 back. When you return 3 back, what happens? Who called 3? So one's right made a call to create this tree. So one's right is now going to store the address of 3. So it gets connected here. From here, if you return n, where does it go? It goes back to the constructor because this made a call to create t. Finally, root is referring to the address of 1, right? Okay, I'll hide myself so that you can see. The root is referring to this one, right? So this is how it is happening, right? So this is a small example demonstrating how this small tree is constructed using this code, right? Now I will run this code on a bigger example as well. Now some of you might not be convinced that whether this code will work for a bigger tree or not. So let us rerun this code on a bigger example. Okay, so this is the method create tree that again I'm explaining with a big example. So let's say I have a tree which should be built like this. Let's say I have 1, I have 2, I have 3, I have 4, I have 5, and maybe I have 6. Now what input should I give? So first of all, I will give the root node. Okay, so input will be 1. Then I will go left. Input will be 2. Then again I will go left. The input will be 4. Then I will go left of 4, which is -1. I will go right of 4, which is also -1. Okay, then I will come back because 4 is done. I will come back. I will go in the right of 2. So right of 2 is again -1. Then I will go back. 2's left is done, 2's right is done, right? So I'll go in the right of 1. So right of 1 is 3. Then I will go in the left of 3, which is 5. I will go in the left of 5, which is -1. Right of 5, which is also -1. Then I will go back. I will go in the right of 3, which is 6. Then left of 6, right of 6. -1, -1, right? So the goal is, given this input, I want to create this tree structure in the output. From this input, I want to create this tree structure, right? Now let us see how we are going to do it. So again, I'm going to read some data. So I will read the first number, that is 1. I will say fine, data is equal to scanner.nextInt. It's not -1. So I create a new node n, right? So fine, let's create a new node and that is having data 1. Let me draw the stack as well side by side. So n is referring here, right? Now so if you want to learn what is the function that is currently executing, so that is at the top of the stack. So n is created. Now you make a call, n.left equal to create tree. So you're making a call to create something in the left of 1, right? So 1 makes a call for the left part. So again, you go call this function, you read data. So data is the next number, that is 2. Fine. You again create a new node. Now this function is paused. This function is paused here. You said fine, I'm going to create a new node and that node is 2. That node is 2. Right node is not connected. It's not connected with 1. Right? And again, you say I want to connect something in the left of 2. What will be that something? Again, you make a function called to create tree. So again, this is paused and it is expecting to build its left tree. So you again call the function create tree, you read the data. So now you're going to read 4. So you read 4. You read 4. Now 4 says, okay, I'm a new node and I will create something in my left. A 4's left makes a call to create tree. The 4's left again makes a call to create tree. And in this case, you read data. The data comes out to be -1. And if the data is -1, you return null. The 4's left gets to know that my value is null. Right? So a null is returned from this function, which is attached with left of 4. And then you hit this line for the first time in this function call, right? N.write, this is equal to create tree. Now you say, okay, I will again call create tree. I will read this number. This number is again -1. it returns a null in the right also. 4's left and right, they are null. That means the subtree of 4 has been created. This subtree is finished. I will return n. This is null and I will return n. So n is this. Now where this return value will go? It will go back to the place from where it was called. So who called it? 2's left called it. So 2's left is now connected with 4 and this function call is over, right? So 2's left is connected with 4, right? Now this is the point where this connection has been established, right? So 2 made a call to 4. 4 said, okay, I will build myself. I will build my left and right, which are null. And now I will return myself, right? So 2's left is over. Now what will happen? 2 will make a call on the right subtree. So 2 makes a call here, n dot right, this is equal to create tree. Now what do I read next? Again, it is -1. So I return a null. I return a null from here. So 2's right is null. So 2's right is null. It's not referring to anything, right? So this value is null. Now 2's left is done, 2's right is done. I say return n. So return n means what is the function that is at the top? At the top, I have this function. So I'm going to return this subtree, this whole subtree back to 1. So basically, 1 will get to know that my left points to this n, and hence the left subtree of 1 has been built. Now I will build the right subtree, right? Okay. So 1 will say, okay, fine, my left subtree has been built. This is over from the call stack. So once 1 is now connected with 2 and 4, right? This tree. 1 will say, okay, now it is my turn to call the right. So once left is done, it will execute this line. N dot right, this is equal to create tree. Now you again make a call. Next number you read is 3. So you create a new node called n. This is the new node. So 3 is created. And then you again make a call to the left. So you read a number, 5 is created. This is new node. Then you again make a call to the left, -1. So 5's left is null. Again you make a call on the right. So 5's left is null. Again you read -1. So 5's right is also null. Then you return n. So you return 5. So 5 gets attached in the left of 3. So 5 is returned. It gets attached in the left of 3. So 5 goes here. Right? Then again, what's going to happen? You will say, okay, I want to build something on the right of 3. So 3's left is done. 3's right's done. So I'll again make a call. It will read 6. A new node will be created 6. Okay. And again, you say, okay, I will read the left, which is -1. I'll read the right, which is also -1. And then I will return n. When you return n, this 6 is returned back to the right of 3. So this 6 is being attached here. Right? And then you say, okay, I'm going to return n. So when you return n, you return this 3 back to 1. So once right is going to point to this subtree 3, 5, and this subtree is attached with 1. So finally, when you are here, this call is over, right? So you will return n. So n will be this node, and it is returned back here, root equal to create tree. This becomes the root of the tree. So root is a data member of the class, and hence root of the tree gets updated. I hope you are now convinced that how this structure can be made so easily with this recursive function. Okay, with this recursive function. Okay, now this way of building the tree, it is called as pre-order, right? Pre-order means first we are building the root node, then we are building the left subtree, and then we are building the right subtree. Then we are building the right subtree, right? So right now we have built the tree using a pre-order recursive build tree function, right? Or create tree function, right? Next we will look at how we can print this tree in a similar way. Now let us talk about tree traversals. Okay, so tree traversal is a way to iterate over all the nodes of the tree, right? Now this traversal can be helpful if you want to perform operations like counting the number of nodes, searching for a given node, updating a given node, right? So in order to do all these operations, we must know how to traverse a given tree, right? So a tree has been built, a tree has been created. We want a way to go to each and every node of the tree, right? So as I discussed, if you want to do a tree traversal, there are two broad techniques, right? So tree traversal, right? So one is your recursive technique, that okay, you start with the root node, then you iterate recursively on the left tree and the right tree, right? There is a recursive way of doing it. There is a iterative way of doing it, right? So we will discuss all these ways now, right? So in recursive way, again, there are it depends upon the ordering. Okay, the way is same. We basically recursively iterate on the left and right subtrees, but based upon ordering, there are three different ways. One is called as pre-order traversal, one is called as in-order traversal, and one is called as post-order traversal. We will be looking at all of them. In iterative, there is only one way, that is called as level order traversal, right? So all of these traversals, they are going to travel all the nodes, but the order in which you will see the output, it will be different. So let us start with the pre-order traversal, given this as the tree, right? 1 2 3 4 5 6. So I will just redraw this tree. 1 2 3 4 5. Now what does this pre-order traversal says? That fine, what I will do, I will travel the root node, then I will recursively traverse the left subtree. Okay, this will be a recursive call, and I will recursively travel the right subtree, again a recursive call. Okay, it is very similar to the build function, what we are doing in the build function also. If you look carefully, we are first building the root node, and then we are recursively building the left tree, and then we are recursively building the right tree, right? So if you see in this case, the output will be very similar to the order in which you have built the tree. So if you start traversing, you will say fine, I will start with the root node, I will print 1, I will go to the left subtree. So this whole is my left subtree. So I will print the root node, that is 2, and then I will go to the left subtree. So left of 2 is 4. So I will print 4 and I will go to the left. Now left is null. So I come back. I will go to the right. Right is null. I come back. Now 4 is done. This whole tree has been printed. So I come back to 2. So I will go to the right of 2. Again it is null. I'll come back. So this whole tree has been printed. I go back. Now left of 1 has been printed. So I go to the right of 1. So I come to 3. I will print 3. I will go left. Now I'll print 5. I will go left. I'll print right of 5. Again null. So 5 is done. So this whole tree has been printed. So I'll go back. So at 3 I'll say okay, let's go right. I'll print 6. I'll go left. I'll go right. Nothing happens. This whole tree has been printed. I come back. Now 3 has been printed. So root has been done. Left of 3 has been done. Right of 3 has been done. So I'll return. So this whole tree has been printed. I come back. And at 1 I see 1 has been printed already, because before printing left and right I print 1. This output is called as pre-order output, in which before printing left and right nodes I print the root node, right? So 1 2 4 3 5 6. This will be the pre-order output for this tree, right? Now let us see this thing in our code as well. Let's write a pre-order print method. Let's write a method called void display, and this is going to be the method that will display the tree, right? So inside this logic can be changed. I can display a tree in a pre-order way or in a level order way or any other way, right? So I'll again create one more helper method. So I will say void pre-order. So void pre-order print. Now this is a recursive function, so I have to tell at what node I'm currently at. So I will start with the some node, that is root node. Okay. So what I will do, I'll say fine, I will have a base case. What will be my base case? What is the smallest tree I can get? That the tree is null, the root is null. In that case, I don't need to print anything. I will simply return. Otherwise, what I will do, I'll print the root data and I will go on the left and the right tree. So I'll say fine sout root dot data, go and print the left subtree recursively. So pre-order print root dot left, then pre-order print root dot right. That's it. And in the display method, I can call pre-order print with the root of the. Now let's do one thing. Let us test our binary tree, because we have the create method, we have the print method. Now I can create a binary tree and try to print it. So I can say fine, I want to create a binary tree object. This is equal to new binary tree. I have defined the class. Now as soon as this constructor is called, your tree will start getting built, because we call the create tree method here, right? Now I can call t.display, right? Now think of any tree that you want to make. We will give it as an input here. Sorry, I should run this file. Now this is waiting for the input, right? So let me draw a tree. Let's say tree is 1, 2, 3, 4, 5, 6, right? Now how this tree will be given as input? So you will input 1, then 2, then 4, then left of 4 minus 1, right of 4 minus 1, right of 2 minus 1, then 3, then you will input 5, left of 5, right of 5, right of 6, right of 3, that is 6, left of 6, and right of 6. Okay, the same input that I have shown you in the example also, this input is given. And now I'm saying that let me print this tree. What I'm getting, I'm printing 1, I go here, then I go to 2, fine, then I go to 4, fine, then I go to 3, I come back, I go here, yes, then I go here 5, then I go here 6. Absolutely correct, right? So if you look at, this was a pre-order build, right? And this is actually a pre-order print. So if you see, the output will be exactly same. 1, 1, 2, 2, 4, 4. Minus 1 I'm not printing. Skip, skip, skip. Then 3, 5, 3, 5. Absolutely correct. Minus 1 I'm not printing. 6, 6, right? That means my both functions are working fine. Tree is getting built correctly and tree is also getting printed correctly as well, right? Now I will show you two more variations of this print method, that is called in order print and post order print. So now let us discuss the next type of recursive printing that we call as in order print. Okay, so I hope pre-order is clear. Now we are moving to in order. So nothing is going to change. The order of printing is going to change. Okay, so earlier it was root, left subtree and right subtree. Now what we are going to do, in order means root will be printed in between. So before you print the root, you will print the left subtree. Okay, and after you print the root, you will print the right subtree. That is what the in order printing would mean. Now let us dry run this logic on our code and see what do we get in order. So what I want to do, so I will start from the root node. I want to print this root node, but before that I will have to print the left subtree, right? Now at the left subtree, again, if I am at 2, I have to print the left subtree. So that means I will have to print 4. So 4 will be the first output that I will get. Now I will print the root. So what is the root? The root is 2. All right. Then I will print the right subtree. So right subtree of 2 is null, right? Then I can go back to 1. So for 1, I have seen the left subtree is already printed. Then I can print the root. So I will print 1. And then I will print the right subtree. Now I am at 3, right? Before I print 3, I will have to print the left subtree. So only one node, I will print 5. Then I can print the root node, that is 3. Then I can print the right subtree, that is 6, right? This will be the output we can expect by traversing this tree in a in order fashion. So let us jump into the code and see what we will change, right? Just like the pre-order print method, what I will do, I will create one more method called as in order print. So in this case, the root will be printed in the middle, and this call will be now in order print root dot left, and this will be now in order print root dot right. Okay, now in the display method, instead of calling pre-order print, maybe let's just call in order print this time. I want to display the tree using in order print. I will pass the root of the tree as a parameter here, right? So let us give the input for this tree and see what output we get. We are getting 421536. Is it the expected output? 421536. The answer is yes, right? Now you might be interested in doing a call stack analysis of this, right? So let us see how we can do the call stack analysis as well, right? So in the beginning, what is happening? Let me also copy paste the code. This is the code, right? Let us do the call stack analysis. This is the method that we are calling, right? So the call stack is empty, so we called in order print where the root node is 1. So I say root is 1, but I'm not going to print it. So root is not null. I will just call on the left. So I make a call here, right? So that means root is now 2. I'm at this node, but I'm not going to print it. Again, I make a call on the left. That means root is 4. Okay. I'm not going to print it because root is not null. Again, I make a call on the left. When you make a call on the left of 4, you actually come here. This is null. So if this is null, you return. Okay. So you return. Then you make a call. Then you print the root data. So that means you print 4. This is the top of the stack. And this is the root that we are talking about. So you will print 4. Then what's going to happen? You will say, okay, I'll go right. So right is null. Again, you make a call to null and you return. So you come back. So again, you are here. Now for 4, you have done all the 3 things. Left is done, root is done, right is done. So you return. So from here, you go back and this is gone from the stack, right? Now what is the new top, right? How do we come back to 2? This is how we come back to the 2. So the new top is this. Now this is the root node that is currently we are talking about. Have I printed the left? Yes. Have I printed root dot data? No. I will print it now. Have I printed the right? No. So I make a call on the right of 2, that is null, and I again return. Then this is done. So I come back. Now what is the top node? The top node is 1. So have I printed left? Yes. Have I printed root dot data? No. So I will print 1 and I will make a call on the right. So I make a call on this tree, right? So again, you do a similar process. You come at 3, right? So root is 3. Then you make a call on the left. That is root is 5. So 5 left is null. So you print 5. 5 right is null. You come back. So 5 is done. Then you go back. The new top is now 3, right? It was 5. Now it is 3. So 3 says, okay, my left is done. I will print myself and then I will go right. So root will be 6. So you come here, right? So you went here, then you came here, 6. Now root is 6, left and right, they are null. So 6 will get printed, right is null, right? And then 6 will be popped off, right? Then, so for 3, right is also done. So this call is over, right? And you come back at 1. So for 1, left is done, root is done, right is done. So this call is also over, right? Finally, the call stack will be empty and this is the output that you will get, right? So I hope you have understood the in order traversal. Now make a bigger tree and try to generate the output for that particular tree, right? And next I will discuss post order traversal. Let us talk about post order print. So as the name suggests, post means the word after. Okay, so in this case, what we do, we print root in the last. So first we print the left subtree, then we print the right subtree recursively, of course, and after then we print the root, right? So if this is the tree, once again, what I will do, I start with 1, but I have to first go in the left subtree, then I have to go in the right subtree and then print 1, right? So at 2, I again have to print left subtree. That means I will print 4. Right? Then I will print the right subtree. So right of true is null. Then I will print 2. So I will print 2. Right? Then at 1, I have to print left, which is done. I have to print right subtree, and then I will print 2. So at 3, I will say, okay, print left subtree, which is 5. Then print the right subtree, which is 6. Then print the root, that is 3. Now for 1, left subtree is done, right subtree is done. Then I can print the root, that is 1. Right? So this is what the post order output would look like, right? You might be asking, why do we need so many traversals? Okay, for examples, what happens in certain problems is, in certain problems you are expecting that you are expecting output from the left and right subtree. For example, given a tree, I want to calculate the height of the tree, right? For example, I want to calculate what is the height of this tree, right? So in order to calculate height, what you will need? You will need to know that what is the height of the left subtree. Let's say this height is 3. What is the height of the right subtree? This height is 2. Then can you say recursively at this root node, the height is nothing but it is the maximum of left and right. Okay, maximum of the answer that you're getting from left comma right, and one more than that. So can I say the height will be 4? What is this? This is the answer from the left subtree. What is this? This is the answer from right subtree. So what I'm trying to claim is, in order to build the answer at the root node, you need the answers for the left subtree and right subtree, and hence in problems like these you would of course need a post order traversal, right? So that is the idea. When you need answer from the child subtrees to calculate the answer at the root node, you will definitely need post order traversal there, right? So now let us write the code, and then we will do the dry run of that code, right? So writing code is very easy. So I'm in this class. So if root is null, I will return, right? Then what I will do, I'll go on the left, post order root dot left. Then I can say post order print root dot right, and then I will print the root node. So s out root dot data, right? Now let us go and call post order print in our display method, right? So I can just pass the root here. So t dot display, it's calling the post order print method. Now for the same input, let's copy this input, and we will see what output do we really get. Now we have given the input. I'm getting 425631. Is it the same output as we have got? 425631. Absolutely yes. Now let us do a quick call stack analysis of this method as well. So I'll copy the code. I'll put it here, and let us do a quick call stack analysis. Let's say this is my call stack. In the beginning, I give 1 as my root node. The root is 1. Then I say, okay, make a call on the left. So my root is 2. I make a call here. Now code is paused. Right call will happen later. Again, at 2, I make a call on the left. I come here. Root is 4. A 4 makes a call on the left. So left is null. I return. Then 4 makes a call on the right. Right is null. Again, I make a call and return. Now I can say print root dot data. I will print root dot data. This is the top of my stack. I will print 4, right? Then if 4 is gone from the stack, what is the new top? The new top is 2, right? That means I am in this function. I am at 2. So I am printed the left. I make a call on the right. So 2 says, okay, go and print the right. Right subtree is null. I return. Then what happens? Left and right, they are done. I will print root dot data. That means I will print 2, right? Now 2 is also gone. We are done. So 1 is at the top of the stack. Now at 1, I said, okay, go left, which is already done. Left is done. Go right. I come here, right? So now 1 makes a call to 3, right? Now 3 says, okay, go left. So 3 makes a call to 5. R5 goes here. and R5 says okay, go left, which is null, go right, which is null, and hence you print 5. So you will get 5 as the next output, right? Now once 5 is gone, you're back again at 3. 3 says okay, my left is done, this is done, I will go right. So I go to root node, that is 6, right? The root becomes 6 in this call. So this is the top. 6 says go left, null, go right, null, and hence you will print 6, right? And then 6 is also gone from the call stack. Then what happens? You are at 3. 3 says okay, my left is done, right is done, I will print root dot data. So I will print 3. I will get print 3. So 3 is also gone from the stack, and now top is at 1. So for 1, left is done, right is done, and hence you will print the root dot data, that is 1, right? So this is the output of the post order print. I hope you have understood post order traversal. Next we are going to discuss the level order traversal. Okay, let us jump into the iterative traversal, which is also known as level order traversal. Okay, so that means we won't be using recursion, we would be using some kind of iteration to iterate on the tree. Okay, some kind of loop, right? So let us take this example of tree once again. And idea is, instead of going in a depth first manner, okay, so in all the traversals that we have done so far, what is happening? We are starting from the root node, we are going here, then we are going here. So all these traversals, they are depth first traversals. That means you first go deeper into the tree, and then that's how you iterate. Okay, so your pre-order, post-order, and in order, they are depth first traversal, right? But now the traversal that we are going to do now, it will be a breadth first traversal. That means if I have a tree like this, I will be going across the breadth of each level, this level, this level, this level, right? That means I can expect an output that is 1, 2, 3, and 4, 5, 6, right? So level order traversal. So this is my level 1, then I am printing level 2, and then I am printing level 3. Okay, what is a level? All the nodes which are at same distance from root node. So level 1, all the nodes are only one node, it is at distance 0 from the root node, or let's say level 0. Level 1, all the nodes are distance 1 from the root node, and this is my level 2. All the nodes are at distance 2 from the root node. Okay, so this is also known as breadth first traversal, right? Breadth first traversal, right? Now let us see how we can achieve this kind of a traversal, right? So let's draw this tree once again. Now if you look carefully, if you start doing any traversal, that is a recursive traversal, right? So from 1 you come to 2, right? And at 2 you do not have a direct way of going to 3, right? So that means with recursion it will be very difficult for us from 2 to go directly to 3, right? And if we go to 3, we don't know a way to come to 4, right? So we cannot go back and forth, right? So how this is achieved? This is achieved by using a concept of a queue data structure. Okay, so what we will do, we will create a queue. The queue, you know, it is a P4 data structure, first in first out. So in the beginning I will push this node in the queue, fine, right? And then I will say okay, like queue dot push root. Now I will pop one node from the queue, so I will pop this node and I will push the children of this node into the queue. So I will print it, output will be 1. This is popped. And what are the children of 1? Children of 1 are 2 and 3, right? Now how do I know the children? Because I'm not going to store an integer value here, I'm going to store the reference of this node, right? So I'm going to say okay, this root is, the address of this node is stored here. So if you know the address, you also know the child values, right? So you know the children are root dot left, root dot right. I will push the reference of 2 and 3 in the queue, right? Next I will again pop one node. I'll say okay, let's remove 2, let us print it, and let us push the children of 2 in the queue. So 2 has only one child, so 4 will be pushed into the queue, right? Again repeat this process, pop one node. So now you're going to see that okay, 1 is done, 2 is done. The next node is coming is 3, right? So I will pop it, I will print it, and I will push the children of this 3, okay, into the queue. So I will push 5, 6. So you look carefully. When the second level or the first level is popped, the next level is already in the queue, right? The next level is already in the queue. Let's say I have some more nodes. Let's say I have 7, 8, and 9, right? So let us just extend this example a little bit. Now I will pop 4, I will print 4, this will be removed. 4 does not have any children, so nothing will be pushed. Next I will pop 5, I will print 5, and I will push the children of 5 into the queue. So I will push 7 and 8 into the queue, right? Next I will pop 6, I will print 6, and I will push the children of 6 into the queue. So 9 will get into the queue. Next I will pop 7, I will print 7, and no children, so nothing will happen. Next I will pop 8, print 8, no children, nothing will happen. I will pop 9, print 9, and the queue is empty, right? So no children, so queue is now empty. This will be my output of level order traversal, right? I hope you're convinced that this is the correct output for this tree, right? Now let us look at this implementation in our code as well. Let us discuss the implementation of level order print. So I'm going to create a method called as void level order print, and first of all I will need a queue object, right? And I also need to pass the root here. So I'll say okay, fine, I'll need a queue of node called queue. This is equal to new linked list. So in Java, queue is an interface and linked list is a class that implements the methods of the queue, right? We need to import this from the util package. Okay, so linked list is imported, queue interface is also imported. So to start with, you can say okay, queue dot offer, that is your add operation, right? And I can offer root inside the queue, that means I can add queue, right? Now I said you will do some work while the queue is not empty. So while the queue is not empty, what you will do, you will pop out something. You will say okay, give me the node which is at the front of the queue. So node f, this is equal to queue dot whole, right? So this removes the first node. Like we have seen in the diagram, we are always removing the node at the front of the queue, right? So this is going to remove it and return it, right? Now I can print the data of this node. So I can say sout f dot data, and now I can check if the left and the right child, if they are not null, I can push them into the queue. If f dot left is not null, I will say q dot push q dot offer f dot left, and if the right child is not null, or if the right child is not null, I can say q dot offer f dot right. So in this way, queue is getting filled using these if conditions, and it is getting empty from the front using this whole operation, right? That's all. That is the code, and now I can just run this code in the display method, or here I can say t dot level order print. Okay, root. So it's better to call it internally, because root, I don't want to access it outside. So okay, I'll just call it from the display method because we are testing the functionality. So I can say level order print. So here I can just call t dot display. So now my tree will be displayed in a level order fashion. Let's see what output do we get. So for the given tree, I'm getting 1, 2, 3, 4, 5, 6, which is correct. And if you look carefully here, For this tree, I'm getting 1, 2, 3, 4, 5, 6. Yeah, this is the tree actually. So I'm getting the correct output, which is this. So I hope you understand the level order traversal and how it is achieved using the queue data structure. The code is very simple, and you can also do a dry run of this code at your own, right? Thanks a lot. With this, we come to an end for today's video. Before you leave, make sure you subscribe the channel, like the video, share it with your friends, and I'll see you next time with more such insightful videos.